Hello, everyone. Hello again. This is the third video that I wanted to record. And as I said, for this last one, I chose a few problems from the homework. Some of them are from future homework assignments, but I still chose them because I think they are a good example of what is more or less what I want you guys to be able to do for the exam. Right? So we are going to start with problems from homework 5A. All right, so let's get started. I'm going to start sharing my screen. One note. And okay, so first problem, this is problem 6 from homework 5A. And here we have the scenario of a cancerous tumor that is growing. Okay, and we have this expression here, V of R, and it's described as the volume of a spherical cancerous tumor is given by the function, and then this is the formula that they give us, right? And this is a function that gives us the volume of the tumor, and it's based on the size of the radius. All right, and it's spherical, so you may already notice the connection with the formula of the volume of a sphere, right? And here it says where R is the radius of the tumor in centimeters, find the rate of change in the volume of the tumor with respect to its radius under the following conditions. Okay, so this may sound a bit like a related rates problem. It's not, okay, because first of all, the main difference between this problem and a related rates problem is that this problem involves a function that doesn't depend on time. Okay, it's just we're talking about the radius and the volume of the sphere, right, of the spherical tumor. Okay, so one thing to notice here is that R is the free variable of this function. Okay, so when we were taking derivatives before, it was doing ddx of whatever function we're working with, right, or ddt. Well, in this case, because the free variable is R, then we are doing ddr. Okay, so as a note here, note R is our free variable, right? Then taking derivatives, it's the same as doing ddr of stuff, right? Of whatever functions we're differentiating. Okay, so if we are then finding, it said find the rate of change in the volume of the tumor with respect to its radius. So we are going after the derivative of V with respect to R, right? So we are doing DDR of V of R equals to DDR of the expression here, 4/3 pi R cubed. Okay, so this is just the derivative of V with respect to R, so dV dr, which you could also write as V prime. Okay, or you could write, V prime of R. Okay, and then when we take the derivative of this, well, we just use the same rules we have been using so far. We see R here as our X. Okay, so then 4/3 and pi are both constants multiplying the expression, so we can not worry about them and just do ddr of R cubed, right? But then ddr of R cubed, that is what we need to do power rule there, right? And we get 3R squared. And we would do dr, but R is our free variable already, so we don't do that. Okay, so then we can simplify this a little bit more. The 3 and the 3 cancel each other out. Then we have 4 pi R squared, and that's our rate of change. Okay, that's the rate of change of the volume of the tumor for whatever radius we have. So, and then it says, well, they want us to find that rate of change, but for specific radius, for specific radii, right? 8/9 of a centimeters and then 7/6 of a centimeter. So what we need to do for A and B, we just need to plug in those values for R, right? So we need to do V prime of 8/9, which is going to be the same as 4 pi times 8/9 squared, right? So what is that? We just need to square both the numerator and the denominator, and we get 64 divided by 81, right? And can we do any more simplifications here? No, right? I mean, we can, by that I meant any canceling. No, we can just go ahead and multiply 4 times 64. That is going to be 240 plus 16, 256. 256 pi divided by, oh, sorry. Yeah, that's really bad line there. I don't know why I threw that. 81. Okay, and so that's for A. Now for B, sorry, shouldn't be an equal. For B, we are doing V prime of 7/6. Again, we're just doing 4 pi and then that number squared. Well, 4 pi and that number squared is going to be 49 divided by 36. We can cancel out this 4 and this 36. This becomes 9, right? And then we have the 49 and the 9. We cannot do any more reductions. And then so we get 49 pi divided by 9. And that should be our answers. Right now, if we are worried about the units now, well, we're looking at the rate of change of the volume. Well, volume, the units for volume, it's centimeters, centimeters cubed, right? That's for the volume. Now, because we are doing with the derivative with respect to the radius, the unit for the radius is centimeters, right? So then the units for this one will be, well, the unit of the volume divided by the unit of the radius. Well, then the unit will be centimeters cubed by centimeter, and same over here, centimeters cubed by centimeter. It's a very weird unit, right? Because it makes you want to, like, you know, cancel the 3 and cancel the centimeters and end up with centimeter squared. But centimeter squared will be area. And, you know, using a unit of area to talk about a rate of change in the volume with respect to a radius wouldn't make any sense, right? That's why they don't make that reduction. But I'm sure you have seen that the unit in the answer box of the problem was this centimeter cubed by centimeter. Okay, so let's then go and do this other one, this other problem. We need to find the derivative of the function f of x equals x plus square root of 3x, all of that divided by 3x minus 4. Okay, so well, this is going to be the quotient, right? Because we have, I mean, function over a function, it's a quotient rule. So remainder of the quotient rule, f over g, the derivative of that is f prime g minus f g prime divided by g squared, right? Okay, now, before we go ahead and start the derivative, it's going to be useful to rewrite this expression, okay? We want to rewrite that square root as a power 1/2. All right, but we want to be careful with that because there is a 3 also involved in it. So for that, remember that this, when you are taking the square root of a product, 2 things multiplying each other. You can split the square root. You can split this into square root of 3 times square root of x. Now, you cannot do this if what you have inside the square root is a sum. If you have a plus b like this inside the square root, that is not the same as square root of a plus square root of b, okay? They are not the same thing. People will make this mistake. I don't know, maybe, but I wanted to state it here so that maybe I could keep you from making that mistake. Okay, it's not true with plus, but it is true with multiplication or division. Okay, so then I can come over here and write x plus square root of 3. Then I will do a square root of x, but instead of doing that, I'm going to write x raised to 1/2. Okay, so that I now have something that looks like a constant times a power, because I can deal with that more easily with my differentiation rules. And then we divide by 3x minus 4. Okay, so then let's go ahead and do the derivative. We have to do the derivative of the top function, which is this, right? So x plus square root of 3x raised to 1/2, derivative of that, times second one without, untouched. So there it is, minus first one untouched, times second one differentiated. Well, the derivative of 3x minus 4, that's 3. Right? And then, well, okay, yeah, let's not skip steps, okay? Let's not do yet the derivative there. Let's write it as prime. And then we divide by 3x minus 4 squared. Okay. All right, derivative of this first bracket, set of brackets. Well, x is just 1, and then we get square root of 3, and then for this power, we need to do power rule. So for 1/2 comes to the front multiplying. We have x, and then the new power is negative 1/2, right? 1/2 minus 1, that's minus 1/2. And then we have 3x minus 4, and then minus, and here we have this, and the derivative of 3x minus 4, that's 3. And again, we are dividing by 3x minus 4 squared. All right, what can we do now? Let me see what I had done before. We can split this. I mean, there isn't really much simplification that we can do. What I did next was, you know, collecting this. Well, I guess splitting the numerator into 2 parts. So these 2 parts, and then using those 2 to split the fraction, you know, into 2 fractions, because I mean, with the same denominator, right? So that's what I did. That's what I plan to do. Because, you know, if I do that, let's see, let me show you. 1 plus square root of 3. Well, let's combine those 2. Square root of 3 divided by 2, and then we have x raised to negative 1/2, and then 3x minus 4, and then divided by 3x minus 4 squared. So when you have those 3x minus 4, you can cancel this one out, and you are left with 1 over there, right? So that's going to lead to a simplification of some sort. Let's not rewrite, you know, let's remember that x raised to negative 1/2 is the same as 1 over square root of x, right? So let's do that over here and rewrite this whole thing, okay? We get 1 plus, well, square root of x is now in the denominator. So I will multiply 2, right? So then we would have square root of 3 divided by 2 square root of x. Okay, and that's what we have now in the parentheses. And we no longer have the 3x minus 4 there, and we are now dividing by a single 3x minus 4. All right. Now on the other one didn't have really any more, you know, it doesn't have any other 3x minus 4, so there's not going to be the canceling that we just did. So we will just write the expression as it is. X plus square root of 3. I mean, we can put back the square root of x into square root of 3. So 3x, like this. And then times 3. and then divided by 3x minus 4 squared. Okay, so I mean, yeah, you see, like, you know, you compare this one and this one, there isn't really much of a simplification that has been done, right? So yeah, that was just so that, you know, so that I also give you guys a review on, you know, if you wanted to do the simplifications, how you should proceed and how careful you want to be with those things. Okay, so that's all for the problems that I chose from homework 5A. Now for homework 5B, 6B, I also chose two problems, problem 3 and problem 5. Okay, so for problem 3, it says find an equation of the tangent line to the graph of function at the given point. We have done problems like this already, like a lot, many of them, right? So for this, I mean, all you need to do is you need to take the derivative, right? First step, compute f prime of x, which you can do here. And then once you have found the derivative, you want to find the slope, right? Find the slope of that tangent line. Tangent line. Well, to find that slope, you need to plug in, you are going to use your derivative, and you are going to plug in the x value of the point that you're looking at. So that is 2, right? So 2. That's going to be our slope. Okay, and once we have that slope, we then proceed to write the equation of the tangent line. Right, and for that we want to remember the Poinslow formula. Where m is going to be this, and then x1 is 2, and y1 is -4, right? Okay, so yeah, I mean, I guess what's difficult here, maybe it's the derivative. So let's go ahead and do it. We want to do here the product rule because we have two products, I mean, two functions multiplying each other, right? 1 minus x, and then this square. So let's go ahead and do that. So the derivative of the first one is going to be -1 times second one without, that's x squared minus 2 squared, and then plus first one without, that's 1 minus x, and then the derivative of the second one, derivative of this, well, that is a function of squared, so we need to do general power rule, right? So then we have 2 times the inside untouched with power now 1, and then multiply by the derivative of that inside, x squared minus 2. Well, that's just 2x, right? And we get what now? Sorry. We get minus square root minus 2 squared, and then plus, we get here what? We get, let's see, 4x times 1 minus x times x squared minus 2. We can simplify this, pull out x squared minus 2 from both, right? Because there is 1 at least on each term. Yeah, and then minus one of this is left, so x squared minus 2. And then from the other side, from the other term, you're left with 4x and 1 minus x. We can open this up, minus x squared plus 2, right? And then for this, we get plus 4x minus 4x squared. If you combine these now, you get minus 4x squared minus x, that's minus 5x squared. Then plus 4x plus 2, that's what you get. And then this still has the x squared minus 2 multiplying in front. All right, can you factorize this quadratic? Let's see. You would do 5x, and then x, and then 2, and a 1. You want to get to 4. No, I don't think so. I don't think this is factorable. Yeah, no, it's not. Okay, so that will be your derivative. All right. And then you use this expression to, you know, find your slope and then use the point and slope formula to write the equation of the tangent line. I'm not going to do that. I will, because, you know, you guys know already how to do that. Let's just now, I mean, and if you still want to see, you know, how that is done, you can go back to the examples that we saw in class, examples that I assigned for extra exercises, and then the previous video for exam 1. I'm pretty sure I discussed a pattern like this on that. Okay, let's do then this elasticity of demand problem, which we haven't done too much because I don't think they are that important when it comes to, you know, calculus. And also, you know, if this class was mostly economics people, then I would probably give more importance, but that's not the case. I don't think it's fair to focus too much on economics problems. Like, I do want to show you, yeah, guys, yeah, but I also want to show you some other sorts of problems and focus on some other ones as well, and not too much on just this one. But let's see. So for elasticity of demand, we want to remember the following things. We want to remember that, you know, so let's write it here. For elasticity of demand, what do we need to compute elasticity of demand? Well, we need f of p, right? That's the function that we need. And that is going to be given in, you know, at the beginning. And at the beginning, you will be given an equation that relates unit price and demand, x and p, right? And what you would do is you want to take that equation and solve for x. So solve for x, and so you would do whatever you know, you just like isolate x on one side, on, let's say, the left side, and whatever it's on the right side, that you call f of p. Okay, and once you have f of p, then all you need to do next is just remember the formula. Then just remember that the formula for elasticity of demand, which is the function called E of p, that's the name of the function for elasticity of demand, E of p, is equal to minus, and then p times f prime of p divided by f of p. Okay, so once you have found f of p, you need to find f prime of p and then compute E of p. All right, so this function over here, I mean, the equation that we have been given, it's already solved for p. And so for what we have there on the right side, it's f of p. Okay, so let's write it down. F of p is then minus 3/4 p plus 16. Then the derivative of that will be, well, when you're doing this derivative, you want to remember that p here is like x. Is your, what happened? I think there was like a moment when it stopped recording. I hope there were no interruptions. Okay. Let me share again the screen. What? Why is it doing that? Sure. Okay, so, all right, so let's keep going. So this was the derivative. No, this was the f of p. Now we need to find f prime of p. Well, p is the free variable here. So this constant times p, the derivative would just be the constant, right? So minus 3/4. And that's it, because the 16 goes to 0, right? So that's cool. The derivative is just a number, just a constant. So what we need to do next is then plug in the formula for E of P as minus P and then times derivative, which is -3/4, and then divided by the function itself, which is -3/4 P plus 16. We can simplify this a bit more. We can multiply, these two, the two minuses, and you get rid of the minuses, it becomes a plus. So then you have 3/4 P divided by -3/4 P plus 16. Another thing that we can do is this 4 in the denominator, you can actually send it to multiply the whole denominator. So then that will leave us with 3P divided by 4 times 3/4 P plus 16. And then when you distribute that 4, you will cancel out this 4 in this denominator, right? And you will be left with -3P. And then 4 times 16, that's 64. You can rewrite it like this so that it looks a bit better. And that's your expression for elasticity of demand. Okay. All right. So the next thing that you need to do is just plug in a number. F prime of P, we got. E of P, we got also. We just now need to compute E of 5, which means you come to your elasticity of demand function, your E of P that you just found, and you plug in 5 for P. So when you do that, you get 3 times 5 on the numerator, and then 64 minus 3 times 5. 15 divided by 64 minus 15, what is that? That is 15 divided by 49. Yes, 49. Okay, so remember that. Okay, so we need to compute it. We got this fraction, which we cannot simplify anymore or reduce anymore. So that you can enter already as your answer, 15 divided by 49. And then it says, determine whether the demand is elastic, unitary, or inelastic at the price P equals 5. Well, that, remember, that it depended on whether it's bigger than 1, less than 1, or equal to 1, right? This is obviously less than 1, because in this fraction, the denominator is bigger than the numerator, right? So this is going to be less than 1, which means that it's inelastic. Okay, so that's it for problem 6b. I don't think anything else will be asked about a demand and elasticity of demand problem, besides maybe interpreting this result, right? Which, as you all remember, let me write here the interpretation. So E of 5 would be the drop percentage-wise in demand if we decided to increase the price of P equals 5 by 1%. Okay, that's how you interpret this result. All right, let's go ahead and do problem 7. So a few problems from homework 7A. Let's see, is this only one problem? Yeah, it's only one problem. Yep. Okay, so homework 7A, find the first and second derivatives of the function. All right, f prime of x. Okay, so this is a quotient, right? X divided by 8x plus 5, that's a quotient. So yeah, let's just go ahead and do that. So the derivative of the first one, that's 1, times second one without, 8x plus 5, minus first one without, that's just x, and then the derivative of the second one, that's 8. And then we divide by the second one squared, right? So 8x plus 5 squared. You see that you can simplify what's in the numerator. You distribute the, you multiply 1 and 8x plus 5, you get 8x plus 5. And then you can distribute this negative and the 8x here, minus 8x, still 8x plus 5 squared. You see that this 8x and this minus 8x cancel each other out, and you're left with this 5 divided by 8x plus 5 squared. All right, so this is where you are going to then differentiate, right? Because you want to find the second derivative. We just found the first one. All right, so you could again do quotient rule, but that's not going to be the easier way to go about this, around this, okay? You want to rewrite this as a power. Well, you see that when you can do that whenever you have a quotient and the numerator is just a number, okay? Like that's when it's convenient. So 5 over here is just 5, and then you write 8x plus 5 with negative power, right? This is going to be easier to differentiate. When you then go ahead and take the second derivative, you do derivative on this, on this, right? So the 5, you disregard it, and then you do general power rule, because this is a function being squared, well, being raised to a power, right? So then you have minus 2 in the front multiplying, then 8x plus 5, new power, negative 3, and then times the derivative of the function, that's 8. And then you can multiply, finish multiplying the numbers. 8 times 5 times negative 2, that's negative 10, plus times 8, that's negative 80. Negative 80. And then you can send back the negative power to the denominator. So 8x plus 5 cubed. And that will be your second derivative. I don't think you can do any more simplification. All right, so that's it. Okay, now 8a and 8b. Okay, so these are two homework problems. Well, I'm going to do 3 there, where I talk about, well, where the reason why I chose them is so that you guys can see examples of me solving problems of the kind, given this function, find where it increases, find where it decreases, find the relative extrema for this function. Okay, so that's the reason why I chose it. I did some of those in class. I still need to do 4.2, which is going to be related to that kind of problem. But these problems that I have chosen here are all about from section 4.1. Okay, so I am not doing any for section 4.2. All right, so problem 7. Find the intervals where the function is increasing and the intervals where it's decreasing. Enter your answers using interval notation. If an answer cannot be expressed as an interval, enter empty or that symbol over there. Okay, so remember that the steps for these are the following. We need to first compute f prime of x, right? So we do the rules that we have been using so far. So 5/3, that's just a constant, so you don't touch it. And then the derivative of 3x cubed, that's 3x squared. And then minus, again, that constant, you don't touch it, 15/2. And then you do the derivative of x squared, which is 2x. Right, so you see that the 3's and the 2's cancel each other out very nicely. And then you're left with 5x squared, and then minus 15x, which you can, rewrite as, well, you see that both terms have coefficients multiples of 5. So you can pull out a 5. You can also pull out an x because you have 2 x's here and you have 1 x here. And so then you're left with x minus 3, right? So that's your derivative. Okay, the second step is to find the roots, right? We want to set the derivative equal to 0. and find those x's that we get. So well, when you do this, you set each term equal to 0, and you get x equals 3, and you get x equals 0, right? And also we need to find x values that make f prime of x not exist. Well, because f prime of x here is this nice polynomial, that means that there is no x value that breaks it, right? Because polynomials behave nicely everywhere. They're continuous everywhere. They don't have interruptions. They don't have points where it blows up to positive infinity or negative infinity or something like that, right? So here, none, right? So then these are the only values, the only x values that we will use in our next step. Our next step is doing sign testing. And for that, we need to draw the x-axis, right? And then spot these two x values, 0 and 3, and use them to split the number line into 3 intervals. And we will need to pick then samples or points from each interval and plug them into the derivative. Remember that the derivative is 5x and then x minus 3. Right? So, okay, so let's pick -1, 1, and 4. So when we test -1, we get what? We get 5x. If you plug in -1 into there, you get a negative number. If you plug in -1 into x minus 3, you get also a negative number, right? So negative times negative, that's positive. So that means that you will get positive sign over here. Now, when you test 1, again, well, 5x, if you plug in 1 there, you get a positive number. If you plug in 1 into x minus 3, you get 1 minus 3, that's negative. So the answer is negative. So this is all negative. And then for 4, 5x, that's positive. 4 into x minus 3, that's positive. So you get positive now. Again. Positive. So remember that positive means increasing. So we are increasing over here and also increasing over here. And we are decreasing over here because of that negative sign, right? So when you write your conclusions, okay, you may not write the word conclusions when you finish off a problem like this, but because the question is about, finding intervals where something happens, then you must state on these intervals, this happens, okay? Like even if that doesn't necessarily mean writing a complete sentence, you should write the intervals and next to them the word increasing or decreasing. Okay, that's like the minimum that I expect from you guys. Okay, so conclusions. The function f of x increases on the intervals because there are 2 of them, right? Negative infinity to 0 and 3 to positive infinity. And it decreases on the interval 0 to 3, right? And that's it. Okay. Yes. All right. So that's the answer for that problem. Okay. Now homework 8B. I chose 2 problems. Okay. So in the first one, we are going to find the relative maxima and minima of the function. And for this, we are going to follow the strategy established by the first derivative test. Okay, so if anything, review, check, or have at hand your notes about first derivative test. Okay, so in that set of steps, you want to first compute f prime of x. Here we get 2x and then -2. And it's going to be maybe better if we write this as 2 times x minus 1. Second, you want to find the critical numbers, right? Remember, critical numbers are x values in the domain of f such that either f prime of x is equal to 0 or f prime of x does not exist. Okay, so f prime of x here is 2 times x minus 1. We can already see that whatever x value we pick, it will never make f prime of x not exist, right? Like any x value works. So then we are not going to find any of this kind. Okay. Now for this kind, yeah, for that we will find some, and we need to set the derivative equal to 0. You divide by 2, you get 0 on the right side still, and then you add 1 and you get 1, right? So that's your only critical number here, right? So then the third step is sign testing. And for that, we just need to draw the x-axis, spot x equals 1 here, and use that to split the number line into 2 intervals, right? And now you pick a number here, let's say 0, a number here, let's pick 2, and you're going to plug them into the derivative. You plug in 0, you get positive and then a negative, and that is negative, right? You get a negative. Now for the other one, for 2, you plug in, you will get a positive here and then a positive parentheses, right? So you get a positive. Okay. Now remember that when you made the conclusions here, right? Conclusions, what you need to be looking at is if you are seeing a change of sign about a critical number. In this case, critical number is 1. And we do see that there is a change of sign, from its right, from its left to its right. We go from negative to positive, which means that the function around x equals 1 is, well, on the left is decreasing and on the right is increasing. So that means that x equals 1, it's a relative minimum, right? So you write f of x has a relative mean at x equals 1. That's it. All right. So that's, and it makes sense, right? Because this function over here, x squared minus 2x, it's a parabola, right? It's a quadratic expression. It's a polynomial of degree 2. So, and then you see that the sign of x squared is positive, right? The number multiplying x squared is positive 1. So that means that this function looks like that. And then it makes sense to say that it has a minimum, right? Well, what we found here is that point over there has x coordinate 1. All right. Okay, so let's then go ahead and do this last example. Here we need to find the relative maxima and relative minima, if any, of the function. Okay, so I chose this example because this is a special case in the sense that, usually I will give a function and there will be a relative minima or a relative maximum, or both, or many of them, right? Well, in this case, I chose this example because this function has none of them. Okay. If you graph this function on Desmos, you see that it looks like, I think it looks like this. So, it's your XY plane. And then you draw this line over here, this dashed line. And then this other one over here. sorry. And then your function looks like, it goes like this, and it goes like this. Okay, so clearly it has no minimum, no maximum, right? Because this goes down on forever, this goes up forever, and then this stays flat, but it never achieves a, you know, on this part of the graph, you never achieve a maximum point because you keep going up, although, you know, by very small steps, you keep going up infinitely, you never stop. So there is no maximum that you achieve and then you come down back again. All right, and then same thing on the left side of the curve. Okay, so this is an example where there is no relative extremum at all. And we will see that. Okay, so first step again for the first derivative test is going to be, you know, taking the derivative. Because this is a quotient, we're going to do quotient rule. So the derivative of the first one, that's 1. The derivative of the second one, that's x plus 3, minus the first one without, and then the derivative of the second one, that's 1. Right? Divided by x plus 3 squared. If you look at what you have here in the numerator, you can open up the parentheses and you get x plus 3 and then minus x. X plus 3 squared. The x and the x minus x cancel each other out. And you get 3 divided by x plus 3 squared. All right. Okay, so what is the next step? The next step is finding critical numbers. Okay, so the first one is going to be when you set up the derivative equal to 0. Well, the derivative we found is 3 divided by x plus 3 squared, right? Well, the thing is that so when you do this, you have no solution, right? Well, look at that. If you look at it, there is no x value that will make the fraction equal to 0, right? The numerator is always 3, and the denominator can never make the fraction equal to 0, right? I mean, you could think of the problematic number of -3, which would make the derivative, the denominator 0, but 3 over 0 is not 0, right? And then any other number will give you some other number that is non-zero. You square that, still non-zero. 3 divided by a non-zero number, still non-zero, right? So there is no solution for this equation over here. Now, I mean, if you wanted to actually do the equation and show by working out the equation that, you get no solution, well, if you wanted to solve for x, you would multiply by x plus 3 squared, right? Just to get rid of that x plus 3 in the denominator, or to move it around somehow. Well, you cancel out, you get 3 on the left, and when you multiply 0 and that, you get 0, right? But then you get the equation 3 equal to 0. That's a contradiction. That's like nonsense, right? So when you arrive to a nonsense result or a contradiction like this one, then there is no solution. Okay, so this means no solution. Okay, so that is one type of critical number, right? A root of the derivative. Now the second kind comes from an x value that makes the derivative not exist, right? Well, notice that x equals -3 makes the derivative not exist, right? Because when you plug in here, when you plug in here -3 for x, you get 3 divided by 0, which is, infinity, or it's not a number, right? But the detail is in that -3, the x value -3 is not in the domain of f of x, right? But x equals -3 is not in the domain of f of x. Because when you come back here and you look at this f of x, if I gave you the problem of find the domain of that function, then you would set the denominator equal to 0, and you get -3, and then you would say domain of f is going to be everything except -3, right? And then of course -3 is not in the domain of f, right? So then -3 cannot be a critical number. All right, so then what does this mean? It means that f of x has no critical numbers, then no relative extrema. Okay, and yeah, that was it. This was that last special example that I wanted to show you guys where we have no relative extrema. All right, so I hope that this video is of help. We will learn in 4.2, we will learn about how to use the second derivative to find relative extrema. And also we'll learn about the idea of concavity, which I plan to include on the exam, but I think that it will suffice with examples that you guys will see in class on Monday and on Tuesday. All right. Okay, so I'm gonna stop sharing and I will stop recording. See you guys on Monday.